Section 4.5 is about properties of logarithms. Starts on page 297. The main idea here is developing ways in which we can legally, let me emphasize that, manipulate a logarithm. So, right there's rules and structure in mathematics, okay? Some structures really well understood, others tend to lead to common errors. So things like a negative times a negative is a positive, right? That is a rule that we use in mathematics, okay? Other rules that you commonly use are like distribution. So if you have 2 times this quantity, you know that means, oh, both the 2 and the y have to be doubled, okay? So that is legal. However, there's some rules that are maybe not as well understood. So this is separate. If I'm squaring a quantity, exponents don't distribute. Coefficients do. So this is not N-O-T, x squared plus y squared. So that's a pretty common error that happens a lot in courses, right? Oh, it seems like if I can distribute this, I can distribute that, okay? So it's all about what is legal. Why is this illegal? Well, think about what you're doing here. You're taking an x plus y and multiplying it by itself. So the x gets distributed to everything in the second fact term, and so does the y. So what I'm really doing here is I'm distributing x, and I'm also distributing y. We usually call this foiling, first outer, inner lasts. So you'll notice it's not just x squared and y squared. I have these outer and inner terms that lead to a final answer of x squared plus 2xy plus y squared. So I can't distribute everything, okay? And we're going to see that kind of come up with logarithms as well. So what is legal to do, what is not legal to do, and trying to understand it so that way it's not memorization. You know, if you understand that this is really just distribution, you'll never make this error, and you'll never lose these silly points on a test, okay? So, because logarithms are closely related to exponents, let's go back to what we can legally do with exponents. Okay, right, this is a legal property from exponents. It says if you're multiplying with the same base, you can rewrite it as one base with addition as the exponent. Here's what's going to happen in the logarithm world. Okay, remember logarithms are the inverse, so we're going to see some nice relationships here, but things are not going to work exactly the same. So here it was 2 logs being multiplied, 2 exponents being multiplied, changed to 1 with addition, okay? So in log land, this looks like 2 logarithms being added instead of 2 being multiplied will equate to a single logarithm that won't have addition on the inside, but will instead have multiplication. Okay, so that's a pretty bizarre property, but it's coming from what we know about exponents. Exponents are simplifying with multiplication of 2 things becomes addition of 1 thing. Here, addition of 2 things becomes multiplication of 1 logarithm. We have something similar with division. Okay, so 2 being divided resulted in 1 with subtraction. Okay, so in log land, we're going to have 2 being subtracted results in 1 being divided, right? 1 logarithm with division on the inside. Okay. Another popular exponent rule has powers raised to further powers, like you're taking an exponent to another exponent, and that's simplified with multiplication. So what could that possibly look like over here? Okay, this one's maybe a little bit more challenging, but what we're thinking about doing is taking a log, raising it to a power. So I'm taking the log base a of x to the y. Okay, and instead of multiplying to simplify, think about how multiplication changed over here. Okay, multiplication changed to addition. So that's what's going to happen. I'm going to end up with repeated addition. Repeated addition is just multiplication. So I'm going to have y times the quantity log base A of x, okay? One way to sort of visualize what's going on here, this exponent comes down and becomes a coefficient in front of the entire logarithm, okay? You can kind of see that up here, okay? So if I just make a modification, if I have these both being x, then another way to write this would be log base A of x squared is equal to, well, if this is the same term, well, it's equal to 2 logs of x. And that is an example of this rule with y being 2, okay? Let me go back and change this so it's generic again, and we can use it whenever we want. But 3 could really follow from 1, okay? So if we just understand 1 and 2, I think we can develop an understanding for what 3 is trying to say, okay? So these are the 3 properties we're going to use. I'll try to leave the 3 log properties up here, and then we'll look at what a potential problem might ask you to do. Okay, so a potential problem might say, expand the following logarithm. So if it's log base 4 of the quantity x cubed square root of y all over z squared. Okay, so this is not normally a direction you're familiar seeing. Expand just means I'm going to build it up. Right now it's very simplified, very compact, a single logarithm. I'm actually going to expand it so it's multiple logarithms. That might be asked if I need to somehow isolate y. Look how buried y is on the interior. So I might have to actually expand so I can figure out what's going on in terms of y, okay? So I see division. Okay, division comes up with this property 2. So I'm going to start by using property 2 and say, okay, I have something that looks like the right-hand side. So I'm going to rewrite it as the left-hand side. My a value is 4. That's my base. My numerator is x cubed root y. My denominator is z squared. Okay, so that's the result of property 2. There's more things I can expand because now I see, oh, these things are being multiplied. So I can now use property 1 in reverse, right? I'm expanding it. I'm going from 1 log to 2 logs. So I have log base 4 of x cubed plus log base 4 of the square root of y. And then there's still this term with z's that I don't need to do anything with. There's still more, right? Think about if I'm trying to get y by itself, I want to kind of keep moving things away from it. I'm going to use property 3. Okay, I see I have a lot of exponents here. An exponent of 3 and exponent of 2. Can you recall what kind of exponent that one's going to be? We're going to use it in a second. And now all those exponents are going to become coefficients. So this is equal to 3 log base 4 plus square root is a 1/2 exponent. So that becomes the coefficient 1/2 log base 4 of y minus 2 log base 4 of z. Okay, so there's our end result of expanding. There's nothing else I can expand here, but if this is equal to something, I could maybe start to isolate y. Okay, so that's how we might actually use that. Before I go on too far, I wanted to show you a non-rule, something that is not legal. And it goes back to our original discussion about when we can use distribution. Coefficients, yes. Exponents, no. What about distributing a logarithm? Okay, so if I have a log of this quantity, that's not a documented rule. That doesn't follow from something from exponents. So I just want us to recall or have seen before that this is not legal, so you prevent silly errors on a test or homework. I cannot distribute the log to both terms. These are not the same thing. Okay, if I can't distribute exponents, I'm not going to be able to distribute logs because they're closely related. So don't make that silly error on tests or on quizzes in the future. Okay, so we've seen an expansion. We've used some of these properties. I want to do 2 additional problems. Okay, these are going to be more equation problems where we have to solve for something. So if I want to solve for x in the following problem. Log base 5 of 2x plus 3 equals log base 5 of 11 plus log base 5 of 3. Okay, so instead of expanding, I'm going to do something slightly different here. I see two logs on this side that I can combine with rule 1. Okay, so I am kind of documenting my rules. You don't have to do that, but if you find it helpful when you look back at your notes, it doesn't take much to write that little 1 up there. So adding two logs means I can rewrite it as one log with multiplication. 11 times 3 is 33. The base of 5 is not changing. Left-hand side, we just went over a non-rule, does not distribute. I cannot have the log of this plus the log of that. So I kind of have to leave the left-hand side alone. But once I'm here, we can use a property that worked in exponents. A single log on the left, a single one on the right. Cancel. Set the interiors equal, and you'll have a solution. Subtract 3. Divide by 2. If you have the time, right, you can always plug that back in. 15 times 2 is 30, plus 3 is 33. And I had 33 on this side, so I knew that I was doing things correctly. But that's the end of that problem, okay? A similar problem may ask you to solve the following. So log base 2 of x plus log base 2 of x plus 2 equals 3. Okay, so notice already how this one differs from the last one. There's no log here. This term is just the number 3. Previous problem, it was log of this, log of that, log of that, okay? So I'm going to have to use a different property here. It's actually a property from the previous video, okay? So log base 2 and log base 2 can be combined, right? Addition in between means I can rewrite it with property 1, and I'll have multiplication on the inside. So x times the quantity x plus 2. Right-hand side, I can't do anything with that. Now, again, different from the last problem. I can't cancel the logs, right? Whatever I do to the left, I have to do to the right. If I try to cancel this, I can't cancel anything here. There's no log there. So this is the point where I'm feeling very stuck. It doesn't look like I can simplify much. I mean, maybe I can distribute my x's, but is that really helping me with this log? So if we're feeling stuck, or we know we need to get to the x, we need to be able to undo the log. So I'm going to use a property from the previous video where we rewrite as an exponential using the definition of a logarithm, okay? This was in the previous one. Hopefully you've got it in your notes. If not, I'm going to highlight it up here because it's that important that we're going to cover it twice. If you have something like a to the y equals x, you can translate it to a logarithm. Logarithms solve for the power. So my exponent of y is now isolated. So I'm looking at something that looks like log base 2, a is 2, of this quantity. Call that quantity x equals 3. Y is 3. I'm going to take all that information and rewrite it as an exponential. Okay? So a is 2, y is 3. My x business is this x times the quantity x plus 2. Now I have like an algebra 2 problem. So I've got to do some distribution. I see on quadratic. We've solved quadratic before. I need to set them equal to 0. Factor or use quadratic formula from here. I think this factors into x plus 4 times the quantity x minus 2. Then set each factor equal to 0. So I get one possible answer of -4 when I set the first factor to 0, and another possible answer equal to 2 when I set the second factor to 0. And I'm not done. I'm not ready to box in an answer yet, and here's why. Another property of log discussed in the previous video. Let's recall that visual. This is what a generic logarithm graph looks like. Its domain is only from 0 to infinity, right? If I think about squishing this into the x-axis, what gets covered, what gets left out? There's nothing happening over here. There's no negative x's allowed. There's no negative x's allowed. This is like an extraneous answer. It doesn't make sense. I cannot plug a -4 into this function. Log base 2 of -4. Try it, you don't have log base 2 in a calculator, but you've got natural log. You can't take natural log of -4. I can't take log base 2 of -4 either. So this is the only real answer. Another way to realize that is to consider, again, thinking about where to put this, maybe just right here in this little corner, log base 2 of -4. If I try to plug that back in as a check, this doesn't make sense. I want to determine that number. Well, that number is some power of 2 that gives you -4. Powers of a positive number are never going to give you a negative number. Square it, square root it. Negative exponents turn into fractions, but they're not going to turn into negative numbers. So that's not possible, okay? So we covered quite a lot about these properties that will allow you to continue to manipulate. The highlight is the definition, and then these 3 right here.